All right. So I'm going to talk about quotient space. So what is quotient space? This is a rather new idea. So basically, the thing we have to talk about is how do you add sets of vectors. All right. So to add two sets of vectors, s plus t, I would just say it's s plus t such that s is an s and t is in t. All right. So that's here we're assuming I'm assuming that s and t are subsets of some vector space V. And oftentimes, we actually like to work with something a little bit more specific than that. We'll actually work with just, say, a point x plus t. And I guess technically you could think about that as being the set containing x, but basically the same definition. It's just x plus t such that, well, t is in t. And so this would be the coset. Turns out this is the coset. Coset of t with representative x. Representative x. And so I just need to prove a few propositions here for you guys that show basically that we can treat these cosets just like they're points. I mean, technically a coset is a set of vectors, right? But I'm going to show you that essentially we can define. Let me just tell you what the definition is, and then we'll prove it's reasonable. So turns out we can show that. Well, goodness gracious, I don't know. It's hard to work in this spot here. Oh well, it's okay. I will make do. It's a sad eraser. Okay, so proposition 7.6.1. Let's get to it. There's basically three propositions we have to prove. Once we get done with those, then we've got a good definition of what a quotient space is, all right? But I need these propositions to make sense of things to start with. Again, V is a vector space. W is a subspace, all right? Let W be a subspace of V. Then x plus W is equal to y plus w if and only if what? If and only if the difference of x and y is an element of the subspace W. Okay, so this is one very important claim that we really need to be able to work with. Now, so critical data here, V is a vector space, W is a subspace. Now, I'm claiming that the equality of those two sets is equivalent to saying the difference is in the subspace. So how should we prove this, Sharon? What do you think?
We should.
It's a biconditional, right? So you have
to prove the forward direction.
Yeah, pick one. Now you say forward. No, I'll go with it. Okay, so let's try the forward direction on for size. So assume what?
Assume x plus w equals y plus w.
Right.
And prove x minus y is an element of w.
Exactly. So if this is equal to that, what's that mean?
That means that x is equal to y.
Well, it doesn't mean that.
No.
But what it does mean is that, well, for one thing, it means that, that means that we have x plus w as a subset of y plus w and vice versa, right?
Okay.
Right. We have that. That's what it means for those to be equal. They're subsets of each other. What's a typical point in x plus w look like? Let's see here how to say it. Well, we define, I've erased it, but typical point in x plus w would be something like x plus, let's say, w1. I think I used w sub x in the proof. So x plus wx would be an element of x plus w, right? Now, how do I know that such a Wx exists? I'm assuming that W is not the zero subspace at the moment. So if W is a zero subspace, right? I think if W is the zero subspace, then this theorem is like, this proposition is automatically true, right? Think about it. If W is a zero subspace, then that means that basically it immediately tells you that x plus the zero vector, y plus the zero vector is just, well, that means x is equal to y, which means that x minus y is 0, and 0 is in W. So it's easy enough to prove the theorem in the case that you have the zero subspace, yeah. So if it's not the zero subspace, that means there's some W sub x in there, right? And then x plus Wx is an element of x plus W. Likewise, however, what?
Y plus Wy?
X plus W, well, yeah, that's also true, but x plus Wx is an element of what, though? Since that's a subset of this, I mean, it means that this is also an element of y plus W, right? I mean, x plus Wx is an element of this, right? But what's that mean? That means that, by definition, there exists, say, a W sub y in W such that what? X plus Wx is equal to y plus W sub y. That's what points in here look like. They have this form for some W. So if I say that x plus Wx is in that set, it means there has to be some point in that set like this that they're equal. And then what does that say? Well, that tells me then just do algebra, right? So what's x minus y is equal to what?
Wx?
Mm-hmm.
Wy minus Wx.
Right, Wy minus Wx. But Wy and Wx are both in the subspace, right? How about difference of points in the subspace? Well, it's a subspace, right? So it's closed under subtraction, addition, lots of stuff. So this is an element of W. What were we trying, but that is exactly what we were trying to show, right? So there you go. I mean, this is not the easiest proof we've done this semester, right? But step at a time, it's, once you have the definitions down and you can work carefully step by step, it's not that hard to do. Okay, I think let's do the other direction then. Find my sad eraser. So the other direction, the converse direction, we assume what?
We assume x minus y is an element of W and try to show that x plus W equals y plus W.
Right. So in order to show that in order to show equality of the sets x plus W, y plus W, we should do something like let's let I'm going to let z be an element of x plus W. My goal at the moment is to show that
in y plus W.
Y plus W, which would then show that, right, x plus W is a subset of y plus W. All right, so one step at a time here. So first of all, z's in there, right? Hence what? Z is equal to x plus, let's say, W, I'll say W1, by definition of the coset, right? By definition of x plus W. And W1 isn't just any of W1, for W1 where? In the subspace, right? Yeah. Okay. Now, let's see here. What else can we do? Oh, I also notice x minus y, an element of W, means that x minus y is equal to, say, W2, which is some element of W, right? It's useful to give it a name to work with, all right? So, all right, what do we got? We have Z is equal to x plus W1, right? My goal is to show that this point is in y plus w, right?
Mm-hmm.
So I want to change this x to a y somehow. How can I do that? Well, let's see here. I've got this to play with, right?
Mm-hmm.
So that means I can solve for x. X is equal to
W2 plus y.
yeah y plus w2, right? Yeah. That's my x, and then plus the w1, right? But of course, that's just equal to, you know, that's
Y plus w.
yeah, y plus I don't know. I mean w3, right? Which is an element of y plus w. Okay. I mean, I know that w3 is for w3 for some w3, which is w1 plus w2, right? I know that that's an element of the subspace because the subspace is closed under addition. So, right. So we've just picked an arbitrary point in x plus w, and we've showed that it's also in y plus w. So therefore, we've shown what?
That x plus w equals y plus w.
Right.
Yeah.
By a similar argument, by almost the same argument.
Y plus w is a subset of.
Right. Because you notice that x and y don't really, I mean, there's a slight difference in the I mean, I have x minus y as opposed to y minus x, right? But you know that if x minus y is in w, then y minus x is also in w because you multiply by minus 1. So there's essentially a symmetry between x and y. So whatever argument I make for x, I can also make for y and vice versa. So anyway, so therefore the cosets are equal as we had hoped. All right. So this gives us like a handy-dandy way to work with cosets, right? To test whether two are equal, I just check if the difference of the representatives is in the subspace by which we're forming the quotient. Okay. I said quotient. I don't know what we mean by quotient yet, but okay. All right. Move along here. I really don't want to hurry too fast through these theorems because they're not hard unless I hurry through them. If I hurry through them, they become hard. If we take our time, they're easy. Fortunately, we had a snow day, so we have all the time in the world. Except that Sharon has some exciting something to do. All right, so next proposition. Oh, come on. What was the next proposition here? Seven point 6.2. Says that x plus w is equal to w if and only if x is an element of w. And again, the context is the same as the last proposition here. We're assuming what? Right, x is an element of V, a vector space, right? And W is what? What do you say?
Subspace.
Yeah, a subspace of V, so. All right. Let's see here. So let's see here. I will start with the forward direction. So suppose that x plus w is equal to w, right? And then what? So hence what? I mean, x
Would
plus.
it be a similar argument as last time?
Yeah, pretty similar. I mean, if x plus w is equal to w, that means that x plus w1 is equal to W2 for some W1 and W2 in the subspace. I mean, it means a lot of things. That's one thing it means. But then what? X is equal to W2 minus W1, which is the difference of things in the subspace, right? Which is an element of W. So therefore X is an element of W. I probably could use proposition 7.6.1 directly here if I had more common sense. Yeah, I think that, I mean, this proof is fine, whatever. I mean, you can look at the proof in the notes, but at this point I'm gonna say forget the proof in the notes. Let's attack this directly. I think we can improve on my notes here. Let's be lazier. Let's be lazier. How can we be lazier? How about this? How about this? Lemma. Zero plus W is equal to W. Right? Mm-hmm. This is true if and only if what? So proof. Let's prove the lemma to start with. So 0 plus W is equal to what? It's equal, I mean, we just do this, let's just do this directly. This is sets of points of the form 0 plus X such that X is in W, right? But that's exactly just X such that X is in W, otherwise known as W. Okay. That's like hardly a lemma. I mean, it's almost just immediate from the notation. Okay, so then so that's my lemma. Let's look at the proof for the proposition 7.6.2. So we have X plus W is equal to 0 plus W, right? By the lemma. No, sorry, I'm in the middle of something. Okay. X plus W is equal. There's no lab. There's no lab.
Okay.
Yeah.
Well, is there class?
There's no class either. No.
Okay.
No. Yeah. So physics. X plus W equals 0 plus W. I told them Wednesday there was no class. Whatever. Okay. X plus W is equal to 0 plus W. What did 7.6.1 say? It's been so long ago I forgot.
If W is a subspace of V, then X plus W equals Y plus W if and only if X minus Y is an element of W.
So X minus 0 is an element of W, right? Which is the same as X an element of W. Okay. And there you go. Oh. All right. So the proof I have in the notes is there's a reason I put that proof in the notes. It's because I think it maybe helps you guys get in tune with the definition of what a coset is and chasing points and subsets and all that. But there is logically a more minimal proof. Here it is. Okay, but the more important thing is, like, you see what's happening here is, as far as these kind of calculations are concerned, if X is in the subspace, it's almost like X is 0, right? Points in the subspace are behaving like 0 in this addition. Is the deeper concept here, which we're working on understanding. Okay. So proposition 7.6.3. What's that one? All right. So exciting. This is our final proposition before we make the definition of a quotient space. All right, so here we go. Again, V is a vector space, W is a subspace. If x1 plus W is equal to x2 plus W, and y1 plus W is equal to y2 plus W, and if C is a real number, although honestly this, we're just trying, as we say, keep it real, but it's not a necessary thing. Then what? Well, here's the punchline. Then x1 plus y1 plus w is equal to x2 plus y2 plus w. All right, and I guess I should put parentheses here maybe. And cx1 plus w is equal to cx2 plus w. And that's so. All right. So how can we prove that? We're going to use the previous two propositions to do it, right?
Mm-hmm.
So let's assume this is thankfully this is a implication. Okay,
Yeah.
so assume what?
Assume all of that top part.
Right. x1 plus w equals x2 plus w.
And y1 plus w equals y2 plus w.
Right. Okay. There we go. And then consider let's see here. Okay, so to show that my goal is to show that, you know, star and star star are equal, right? But what I should do is I should look at the difference of their coset I should look at the difference of their representatives, right? So consider x2 plus y2, right, minus x1 plus y1, right? And while we're at it, let's consider cx1 minus cx2, right? That will help me with these guys. Squiggle, squiggle, showing the squiggles are equal. Okay, so that's representative of the difference of the representative of squiggle left and squiggle right, difference of the star and the star star representatives. What are those equal to though? Well, right, x2 minus x1, right? And
y2 minus y1.
right. And c times x, oh, I'm in 2 and 1, sorry. Now, what do I know about these things that I just wrote, though, here, these differences? See, I'm assuming that x1 plus w is equal to x2 plus w, right? By proposition 7.6.1, I know that x2 minus x1 is in w. And I know that, likewise, I know that y2 minus y1 is in w. So this is equal to, say, wx minus wy, which is again an element of w. And here I'm using by proposition 7.6.1. Right? Likewise, this is an element of w by... Okay, therefore, thus, you know, x1 plus y1 plus w is equal to x2 plus y2 plus w, and cx1 plus w is equal to cx2 plus w. All right, are we good? Okay, so now we have everything we need now to make the definition of the quotient space. Quotient space is a little bit subtle, but it's a really important concept, both in linear algebra and especially abstract applications of linear algebra. It's very important, but it's also, you're just seeing the tip of the iceberg here. The quotient construction also is an important thing that we study in abstract algebra, and so this is perhaps your first real exposure to the idea. That's part of the reason I'm trying to go relatively slow. So here's the definition. But it's not that hard, it's just new. Definition. So again, V is a vector space, W a subspace of that vector space, and we define the quotient space, V mod W. This is the quotient of V by W. Again, the quotient space of V by W to be the set so here's the set. It's simply X plus W. It's the set of cosets of W. X plus W such that X is in V. What?
Can you erase the block?
Oh, I'm free? You've released me
Yeah.
from my box?
Yeah.
I'm out of the box. All right. I'm going to finish this definition in the box, though, and then I will.
Okay.
All right. Then I will free-range lecture. It's very, very exciting. Looking forward to freeing my dotted prison. It's good. Okay. So if this is the quotient space, and of course I'm saying that we're talking about linear algebra, right? So the reason this is interesting is that the quotient space is itself a new vector space. All right, and that new vector space has addition and multiplication defined as follows. So X plus W plus Y plus W is equal to?
X plus Y plus W.
Yep, X plus Y plus W. So that's the definition of addition in the quotient. And guess what? Scalar multiplication, C times X plus W is equal to Cx plus W. There you go, that's the definition.
Scalar multiplication.
Yeah, scalar multiplication. Now, the previous triple of propositions, what they show you is, in fact, that these definitions are well defined. I mean, there's no ambiguity that comes from the choice of representatives, right? I'm working with sets. There's not a unique representative for each coset, so like that begs the question, how can you add them using representatives? If you have different representatives, you know, would the outcome be different? Would it not be a single valued assignment for the addition? Well, it is, because of proposition 3. It says if I choose different representatives, I still get that same set as an output, whether I use 1 or 2. And likewise down here. So we've shown that this definition is reasonable. And then theorem 7.6.5 in my notes. I already claimed in words, but here it is. W, a subspace of V, then V mod W, as defined above, is a vector space over the same field, in our case over R. I will not subject you to the proof, but the proof is simply that the axioms hold. You can go one at a time and basically just chase the axioms through this coset definition. Each one follows through. Like, it's fairly clear. I mean, I'll show you the 0 axiom. That was essentially proposition 2, right? Like, for example, 0 plus W essentially serves as the 0 in this quotient. Let's say 0 in V mod W as 0 plus W plus X plus W is equal to what?
X plus W?
Right, well,
0 plus X plus W?
yeah, 0 plus X plus W, but hey, by definition of the ordinary 0 in the vector space V, I know that that's just X plus W. So check it out, we just showed that this plus anything in the quotient gives you back that same thing, which means that 0 plus W serves as 0. And more to the point, as sets, right, as a set of points, this is just W itself. So And that really is the idea of the quotient. The quotient is essentially saying you take that whole subspace and squash it to 0. That's what the quotient space is. All right, I'm gonna stop the video right here, and I'll start again with examples and the theorem a little bit later. I'm gonna take a break. So.